let's look at question 5. We are told that this is a hovercraft, or otherwise known as an air cushion machine, induces air at atmospheric pressure (1.013 bar) and 30 degrees through vertical axis fan. The air is discharged at high velocity through a skirt or annular gap. The gap is 3 cm as indicated here. The hovercraft weighs 65 kilonewton, and the diameter of the skirt, that is from one end to the other end, the diameter is 8 meters. You're supposed to state all the assumptions before you perform your calculations in the parts B and C. So the assumptions are the assumptions that you would usually use when you have to apply Bernoulli's equation. And in this case, you can see the three significant assumptions that are made are: viscosity effects are negligible, the difference in height between 1 and 2 insignificant, so that we can in fact neglect the gravitational difference, potential difference between point 1 and point 2. Finally, we consider steady state conditions where the flow through the fan passes through the annular gap. Now let's look at part B. After we consider a streamline from 1 to 2. Okay, the pressure within the hovercraft P1 is the weight of the hovercraft divided by the area supporting the weight. Now the area supporting the weight is going to be the peripheral diameter squared multiplied by pi divided by 4, and you're given 65 kilonewton. So you have a pressure of 1.293 kilopascals. Now the big issue at this point is this absolute pressure or relative pressure? Let's look at our hovercraft again. If you study the geometry of the hovercraft, you will notice that there is already atmospheric pressure acting on the hovercraft as shown by my arrows. So, in fact, what we are doing when we calculate this value, we are actually calculating a pressure higher than atmospheric. We can call it gauge pressure. Okay, this is implied in the calculations because we are neglecting the atmospheric pressure effect. So the pressure that is generated to keep the suspension of the hovercraft slightly above atmospheric pressure will be gauge pressure. Okay, let's get back to our solution. Writing our Bernoulli's equation along the streamline from 1 to 2, neglecting Z1 and Z2, we have P1 over rho G of air times P1 over rho G air times G is equal to V squared, where V squared is the velocity of the air exiting. Remember, the pressure P2 is atmospheric pressure or gauge pressure. And remember, our P1, which we calculated here, is our gauge pressure. So that the velocity that we get after crunching our data Using the data extracted from the textbook, the density at that particular temperature, 30 degrees, is about 1.164 kilograms per cubic meter. We will be able to compute the velocity. So our velocity calculations give us 43.13 meters per second square. Now the area of flow is the annular area, which is the circumference of the skirt of the hovercraft multiplied by the h, which is the height above the ground, multiplied by the velocity, and we get 35.52 cubic meters per second. Now the fan power is simply the volumetric flow rate times the pressure, and we are told that the overall fan efficiency is 75%. This gives us 61.2 kilowatts. This takes us to the end of this solution.